Hello, everyone. Welcome back. Today, we're going to learn about correlation. And so our goals are to be able to create and interpret a scatter plot of data. That's actually help us with correlation first. You may have heard of a scatter plot before. Understand the meaning of a correlation between two variables. Be able to calculate the correlation coefficient, and more precisely, be able to use a computer program to calculate that. And be also be used as a hypothesis test to determine if the correlation exists between two variables. We're going to actually get to a correlation. Let's talk about a scatter plot. This is something you've probably seen before. It's a useful tool to see if there appears to be some kind of correlation or some kind of relationship between paired data. So something we think of as being X and a Y. It doesn't necessarily have to be a cause and effect between the two, but see if there's something going on between them. So basically, we plot one variable as X coordinate and the other is a Y coordinate. They want to analyze the graph for trends. So if we look over here at the right, here are some examples of scatter plots. Oops. So essentially, one variable, in each case, is chosen of the paired data shows the X, the other one's chosen as the Y. And then what we're looking for then to see if there are any particular trends we can see. Now, if you notice these things, I'll say correlation. We'll come back to that in a moment. Just look at the pictures right now. If we look at some of these, for example, let's say look at this one first. Okay, this one, if you notice, the data is the points are kind of all over the place. It doesn't necessarily appear to be any kind of particular trend we can tell. Okay, so in that case, we'd probably say that, well, I can't really see any relationship between these two. Let's take a look at this one on the upper left corner. We can see two things are seem to be kind of distinct. One thing does seems to be a increasing trend, at least from left to right. What that means is X gets larger, Y tends to get larger. Okay, that's called a positive. Well, we'll get the correlation in a moment. Basically, it seems to be true that as X gets larger, then Y gets larger, or the other way around. It's also true that as Y gets larger, X tends to get larger. Then also, it seems like the data seem to kind of follow kind of a linear trend, a straight line trend. Now let's take a look at the next one over here in the upper right corner. Once again, we see also they appear to fall much more closely on a straight line, even this one. They look more like a straight line. And also, this is almost like a negative relationship, whereas X increases, X gets bigger, Y tends to decrease, or the other way around. Once again, the same thing is true if you do it the other way. As Y increases, X decreases. And then finally, let's look at this fourth one in the lower right corner. Here, there's definitely a trend. It looks like a parabola, but that's not a linear relationship. So we're going to focus mostly on linear relationships today, although they can be other kinds of relationships. So clearly, it appears to be a relationship, but it's not linear. And we're going to focus on linear correlation today. Now, also, we'll talk about how you can actually do a scatter plot in both StatCrunch and in Excel. Let's do that briefly. And actually, hold on, so let's go into StatCrunch first. So here's some data we'll actually use today. So what we're going to do then is we're going to go first to graph. Then one of the choices then here is scatter plot. Then what we need to do is just check the correct X and Y variables. I'm going to pick these two, X and Y. X for X and Y for Y. And actually, there are a lot of options. We aren't going to focus on those. We just want to hit compute. And that gives us then this picture. Okay. So this is the picture of that data. And once again, why the picture is obviously important is because the pictures give you an idea then of what's going on with the data. And actually, it looks like I might have, hang on a second. Yeah, I think let me take a quick look at my data. I think I may have hit the wrong number somewhere. But anyway, this is what it shows you, the scatter plots. It's basically plotting this paired data. And with that paired data, then it kind of gives you an idea of the trends. It looks like there's definitely an upward trend here. And also, we'll talk about why this value is way up here in a moment. But actually, it looks like as I said, I think I hit the wrong thing. Yes, this is actually be an 8, and it may update automatically. I don't know if it does. Actually, let's do that one more time, because I actually realized I had the wrong data point. Once again, go to graph, scatter, and choose your variables for X and Y for Y. And to compute. There we go, much better. That's what it's supposed to look. Okay, but that's how you do a scatter plot in Excel. And then you take a look at the graph and try to notice what trends you can see. And we'll come back to this one in a moment. Well, now let's take a quick look at the same thing on Excel, how to do that. and also leave the same data, which I probably mean that means I made the same mistake. Let's change that to an 8. There we go. Now, what we do here then is go to insert, the insert menu. So maybe on the home menu, go to the insert menu. And then if you look over here, pick the one that says charts, and then you can pick whatever kind of scatter plot you want. I just pick the first one. And then if you do that, then, oh, sorry, I didn't realize it'd do something first. First, though, you actually have to highlight the data. So you can either kind of drag it across like that. And then once you do that, I apologize, then go to insert, then to charts, and then it's scatter, and then it will give you the same picture, although slightly different format, but the same data. So this is how you do a scatter plot in Excel. And then, because it's a lot of times easier to try to see what trends are there by looking at the data, instead of trying to look at the data in a plot like this, instead of simply the raw data itself. Okay. So what we do then with these scatter plots is try to see if, as I said, if there's some relationship between the data and what kind of characteristic relationship. Does it look like a straight line, look like some other kind of graph? Does it look like it's going up from left to right or down from left to right? And that gets us into what's called a correlation. Let's talk about a correlation. So the correlation exists between two variables when the values of one variable are somehow associated with the values of another variable. That's a pretty vague definition, but basically we're looking for some kind of relationship to see if there's some kind of trend between the two. I'll just read the rest of this. It says, for example, it might be reasonable to think that there would be a correlation between the amount of time someone spends studying for an exam and the score they get in the exam. That's kind of what most of us would expect. We expect to be what's called a positive relationship. The more time you spend studying, the better score you should get, most likely. More hours spent studying would likely result in a higher test score. A linear correlation exists between two variables when there's a correlation that when the data is plotted, the trend, results in a pattern that appears to be approximated by a straight line. Okay, we see that especially in this one right here. Okay, then a scatter plot, as we saw, can help us to see correlation. So first off, our first step in analyzing data like this, paired data, is probably to make a scatter plot, and then we decide based on the scatter plot to see if it looks like there's any kind of relationship there at all, if it's worth spending time on. Now, a correlation, once again, just a relationship. It doesn't prove that there is, it doesn't necessarily imply there is any kind of a cause and effect relationship. That's what it says, just simply trying to see if there's a relationship between them. Now, looking at this, for example, comparing this one to this one, or even any of them, we can certainly look at them and say, okay, this looks like a pretty strong linear relationship, more than that one. But we need some way to quantify that, and that's where the correlation coefficient comes in. So calculate what's called the Pearson correlation coefficient. We call it R. And says the value of R measures, and that should actually be a S, measures the amount of linear correlation in the given sample, measures both strength, strong or weak, okay, basically how well it fits on a line, determining once again talking about a linear correlation, right? How well it fits on a line, and also directions, positive or negative, meaning it's going up from left to right or down from left to right. The correlation coefficient is given by this formula. Now we're not actually going to calculate these by hand. This is how you could do it, where your Z are the Z scores for each X value, and ZX is the Z score for each X value, and ZY, Z score for each Y value. So you have to take your individual columns of data, individual X's, individual Y's, find the means, and then standard deviations, and find the Z scores. You're going to sum up the pairs like this by X and Y pairs and divide by N minus 1, of course, N being the same for both. That's why you have paired data. Now, a few things here. Once again, facts about R, this correlation coefficient, is basically kind of a way to quantify both the strength of the relationship and the direction of the relationship. So the value of R, same thing again, R measures a linear correlation in a given sample. If R is positive, then the correlation is positive. The closer it is to 1, the stronger the positive correlation. Positive correlation means the X values, as the X values increase, the Y values increase. The line goes up from left to right. So that's a good example of this one right over here. Okay. In fact, this is its correlation coefficient, 0.859, which is fairly strong. Once again, what that means, what this number means, is the fact that it's closer to 1 you get, the closer all the data are to lying on a straight line. Okay. So in that term, as you'll see in this one, correlation over here, just think of the absolute value, not negative or positive. This one is stronger than that one in that sense because the data is close to being on a straight line than this one. That's the reason that absolute value of this one, 0.971, is greater than this. Now, 1 being positive means the data goes up from left to right, or it means that as one variable increases, the other one increases in the sample. That's what we see here. That's why we have a positive correlation. Over here, It's negative, meaning that as one variable increases, the other one decreases. And that's what we see. That's called a negative relationship. So once again, if your correlation coefficient is positive, it means as one variable increases, the other one increases. It's negative, as one variable increases, the other one decreases. There's an inverse relationship between them, but it's negative. And I state that both here in the second one. So, and also once again, so the closer it is to 1, the closer the values are to being on a straight line. The closer it is to 0, the further they are from being on a straight line. Yeah, so then it says the closer r is to 0, the weaker the correlation. So if we look at this one right here, we see this is the one we said it appears the data is kind of all over the place. And that's going to reflect in the correlation coefficient, which is fairly close to 0, meaning there's really no, in a measurable sense, there's no significant relationship between these data. And then finally, it says, also note a negative R does not mean weak. It just means unless it's close to 0. That's right. So remember, weakness is about how close to 0 it is, not being positive or negative. And finally, this one right here, which you notice this one has if you do a correlation coefficient for this one, we can find a value, but remember, this is for a linear relationship. So this one is not, even though we can find one for this data, it's not really suitable for this data because clearly there's something nonlinear going on here. Now, there are other ways to do correlations for data like this, for data that might be a parabola, but that's not what we're looking at today. And also, once again, remember, correlation does not mean causation, doesn't imply that. So just because there's a relationship, even possibly a strong relationship, linear relationship between values, like for example, this one, doesn't necessarily imply that one, either X or Y, causes the other one. It just means there's statistically, there's a strong relationship between them, but doesn't mean there's a cause there. There could be other things going on. So how do you use, or why do you use correlations, even if they can't prove cause and effect? A lot of times they're very useful in trying to find relationships between data. So currently, you may have heard of data science. That's a big area these days in statistics and in business as well, lots of fields, because they're trying to look at data you can collect through the internet, through other means, and trying to determine relationships between the data to make predictions. So for example, let's say you own a business, and maybe let's say you make energy bars. So you want to know who to market your bars to. And so you'd probably want to look at data and try to find what things correlate with that. So you'd expect if you make energy bars, it probably correlates with correlations with people who buy, water as opposed to soft drinks, or people who get, the more exercise they get per day or per week would correlate with that as well. It'd be a positive relationship. Okay. You want to find relationships like that because that can then help you predict who will most likely buy your energy bar. And then help you decide who to advertise to. For example, if you want to make a television commercial, that's expensive. So you want to make sure that you have good data and good analysis of that data, find out what correlations you have, so you can make your TV commercial in such a way that it'll appeal to people who are more likely to buy your bar, more likely interested in buying your bar. And also, it could be also correlations, and we're not going to go in this, but also correlations with what's called spatial correlations, maybe where different people live. So you want to be able to market in the places where people are more likely to use your bar. And lots of other ways use this data too. But the idea is to understand data, to understand relationships between data, and also then use that data and those relationships to make predictions then. So that's how it's used in the real world in one way. And finally, we can do a hypothesis test for correlation. So once again, the value R measures the linear correlation of the given sample. You use a symbol called rho, Greek letter rho. It's a Greek letter used to represent the linear correlation of the population. So similar, if you've seen videos on doing hypothesis testing about means proportions, or do similar things. So we're taking samples, assuming they're random samples, then we're trying to then use, if we can, possibly use that sample to imply something about a population. So if there's a strong suggestion there's a correlation in the sample data, we'll try to use that hopefully to imply possibly that there's a correlation in the populations themselves. So in a similar way, we're going to do our null hypothesis H0 is going to be that rho, the population correlation coefficient, is 0. This assumes there's no linear correlation. Once again, that's the proper assumption for a null hypothesis based on these hypotheses of essentially no effect. And then rho is not equal to 0. This kind of assumes that there is a linear correlation. Basically says that there is, if we reject the null hypothesis, then we go with the alternate hypothesis H1 or HA, and that then assumes that there is a linear correlation. Now, We're also going to use the p-value method for this. So it's similar to p-method. If you've seen the p-method value for some of the other videos I've done for testing means and proportions, it's the same concept. So the computer will calculate a p-value for us, and if the p-value is less than the significance level, then we'll go with that. We will accept that correlation. Okay, let's take a look at some examples on the right, and we'll do that. Okay, so number one, let's say using the following data set, construct a scatter plot, calculate the linear correlation coefficient, and then determine whether there's sufficient evidence to support the claim of a linear correlation between two variables. Actually, I forgot to give you significance level. Let's go with 0.05. So let me get to the raw menu. There we go. Also forgot to say, so let's say our significance level .05. So that's our alpha. Okay, now what I've done is let's go do this. You're gonna do this in StatCrunch, and here are the steps below. So I've already set this up in StatCrunch. So here is that data. Okay, so what we're going to do then is go to Stat, go to Regression, then you go to Simple Linear. There are other choices here for other types of graphs. We're going to focus on linear correlations. Then we make sure we choose the correct, as we did for the scatter plot, make sure we choose the correct variable. So I'm going to choose X for X and Y for Y. Okay, and here what we're going to do is we're going to focus on hypothesis tests and concentrate on the slope. And here everything's already set up. So the slope, that's what we're focusing on, is that it's equal to 0, and the null hypothesis is not equal to 0. Then just hit compute. That's all we have to do. And then we take a look. And let's actually, as it did in the past, let's actually copy this. And actually just this, we don't need that down there. And we'll paste this then into our, and actually realize we've got to write our hypotheses. So hypotheses first, let's do that. And actually I realize also we want to do the scatter plot as well. So rho is equal to 0 and the alternate or H1, that rho is not equal to 0. Let's go ahead and paste this. I realize we actually didn't do the scatter plot yet, or actually we did, but let's talk about that as well. So let's paste this in. Okay. Now this actually gives us what's called a regression line. We'll talk about that in a future video. This also gives us the correlation coefficient, all right, 0.816. And then what we'll look for then is for the slope, look at the p-value. Okay. So let's make a couple notes. So our R, small r, we're getting that is right here. That's approximately 0. Let's do 3 places, 816. And the p-value, I want to say the slope p-value is this right here, is 0.0022. Okay, the p-value for the slope. Now let's actually go back to StatCrunch, and actually we already did. Well, let's do it again. So let's do the scatter plot again. So go to Graph, Scatter Plot, and choose X for X, Y for Y, hit Compute. Okay, there's our scatter plot. So we see is that we tend to see looks like a positive relationship in the sense that it's increasing from left to right. So it appears that as one variable increases, the other one increases. We also notice we have this, and also the data fits extremely well in a straight line, except for this one. And that's more or less an outlier. And we wouldn't know that if we hadn't done a scatter plot. That's basically an outlier, okay, most likely. Because notice it doesn't really fit with the rest of the data all that well. Okay, but even with that, if we go back and take a look, then what's going to want to compare. I also should have said our alpha is going to be 0.05. If we compare that, p-value and alpha at 0.0022 and 0.05, clearly that's less. So then we can reject HO, okay? So we can reject the null hypothesis because there's enough evidence to support a claim of a correlation. There's enough evidence to support a claim there's a correlation between the data. Okay, and so that's kind of our process we'll go through. You notice then we have that outlier, so that's something to be aware of, especially that's something you can possibly see when you do your data. In this case, there's still enough evidence to support the idea of a correlation, but actually if you remove that outlier, there'll probably be even more. Now, let's take a look at our second example. And this time let's look at some more meaningful data, not just simply called X and Y. Okay, so over here, this says, listed below are duration times in seconds and the time intervals in minutes to the next eruption for randomly selected eruptions of the Old Faithful Geyser in Yellowstone National Park. You may have heard of Old Faithful. It's a geyser that goes off in pretty regular intervals. And so what we have here is each one in seconds. The first, our top row, is the duration time in seconds of each eruption, of these, once again, these randomly selected eruptions. And then the interval minutes, interval after. So the question is, trying to determine, is there some relationship between how long an eruption lasts and the time until the next eruption? So maybe, if the eruption, maybe you're wondering possibly if the eruption lasts longer, the duration is longer, and maybe there might be a little longer interval afterwards. Maybe this kind of needs to replenish itself in some way. All right. Now also let's go with alpha 0.05. I didn't say here what that should be. That's fine. And once again, I've already, let's take a look at our hypotheses again. So the same hypotheses. So what we're doing then is considering rho, which is our correlation coefficient of these populations, general populations. So the null hypothesis is that there's no relationship, and the alternate is that it's not equal to 0, that there is some relationship. And once again, let's go to StatCrunch. And I already have this data in. This is this data right here. So first off, let's do a scatter plot just to see if it looks like there is reason to believe there could be some relationship. This time my X, let's make sure we can see this, I'm going to choose duration and interval after as my Y. Okay, and that's a choice. You could possibly go the other way because actually the correlation works both way either way. But sometimes if you expect one might be if you expect one might be a cause the other, you can always put that as X, but still it's not a proof of a relationship. All right, so hit compute, and that's our scatter plot. Okay, so what do we see? Well, of course, there's not many data values, only 6 or 7 rather. Looks like there might be kind of an upward trend. Okay, but it's hard to tell. We have some data that are quite, out of the range of the others. So it's really hard to say for sure if there's really anything going on by looking at it. And it's possible some of these could be outliers, but then we just don't know. So let's then do our hypothesis test. So we can leave that up and just go to stat, regression, simple linear, and then choose the same value. So we're going to choose the duration for our X and interval after for our Y, and hit compute. And okay, there we go. Actually, let's go into something we may look at in a future video that actually showed us the what's called a regression line, but that's not important yet. Once again, let's copy this into our Word document and then we'll discuss it. Let me check something on my own. So let's go back and we'll insert that. Okay. Now let's again pick out what we need. So our R correlation coefficient is right here. So this is our R, and it's approximately 0.046, which is, as you imagine, we said that's close to what that means. Once again, that's pretty close to, very close to zero. So what that indicates is that, zero would be a perfect zero, would be no correlation at all. So that's pretty close to that. So that indicates that there's no, statistically, there's very little indication of a correlation. In fact, we should have mentioned this back here. This one, 0.86 in the previous example, was a pretty strong example. It would have been even stronger without that outlier value. Okay, it's also positive. In this case, this is also positive, but it's so close to zero that's not, doesn't have much meaning. Then our p-value, so let's going to find that. That's right here. So it's going to be equal to 0.9214. You can see that's very large. So as usual, we'll compare p-value to alpha, or significance level. And obviously it's going to be larger. It's 0.9214. And alpha is 0.05. So clearly that's larger. In this case, we don't reject HO. Okay, and so this means there's not enough evidence to support the claim of a correlation. I won't write that all the way out. But essentially, more detail say there's not enough evidence to support the claim of a correlation between these two things, between a linear correlation between duration times intervals after times. And also, I should have said linear correlation of a, let me just put a little insert here. Let's just say linear correlation. Not really evidence supporting any other kind of correlation, but to be precise, not of evidence support a linear correlation. And once again, it doesn't apply if there isn't one. It just simply means from the data we have, there's not evidence to imply that. So there's not evidence we see to apply a relationship between the duration of the eruptions and the interval after. Okay. Let's do one more example. And we'll do basically the same way. All right. This one says, classic application of correlation involves association between the temperature, the number of times a cricket chirps in a minute. Listed below are the number of chirps in 1 minute and the corresponding temperatures in Fahrenheit. Is there sufficient evidence to conclude that there is a linear correlation between the number of cricket chirps in 1 minute and the temperature? Okay. And once again, I already have this data. And also, let's choose an alpha. Let's say once again, our alpha is 0.5. It could be other things. The alpha is going to be, write that better. So our alpha be 0.05. And then our hypotheses, once again, just abbreviate that. So H0 is once again to be assuming that the true population correlation, that there is not one, is 0. And then H1 or HA is going to be the true population correlation is not 0, but there is some relationship. As we did before, let's go to StatCrunch. I already have this data set. Let's actually get rid of these, or you can bring them up later. So here's that data. So once again, first, let's actually do a scatter plot. Now, this is one where it would probably make more sense to actually, if we think about the possibility, I'm trying to get this where you can see the data. There we go. Actually make more sense for this one for actually the X to be the temperature. So it doesn't really matter, but because basically we want to think of possibly the cause and effect, and obviously the temperature would cause the number of chirps and not the other way around. Actually, I'm going to do that as my X and chirps as my Y. Just keep that in mind, be consistent. And so here is scatter plot. Now here we can see definitely looks like a positive relationship in the sense that it's as one, the temperature increases, the number of chirps increases. But do they fit in a line? Fairly well. Once again, so this just gives us some idea, some reason to believe there could be a relationship. Okay, could be a positive correlation. So then that's what we want to test. So let's go to stat. regression, simple linear. And then once again, remember, I chose temperature to be my X in this case, and chirps out in 1 minute to be Y. Once again, everything is already set up correctly. So I want the slope, and it's already set up the right way. Hit compute. And once again, let me copy this, and we'll do our hypothesis test. All right, once again, get the information we need. So our correlation coefficient, our R, is 0.8 to 3 decimal places, 0.874, which is pretty high. Then our p-value down here is approximately 0.0046. Yes, I did write alpha. So once again, compare our p-value with alpha, and alpha is 0.05. The p-value is 0.0046, which is clearly less. In fact, we can choose like p-value of 1, that'd also be less. So then we can reject the null hypothesis. And so there's enough evidence to support the claim of a linear relationship or a linear correlation. Okay, and more precisely, we would say between the temperature and the number of times a cricket chirps in 1 minute. Okay, so there's enough evidence we reject at that level. Let me actually go back and do one more thing before we wrap up. Let's take a look at this again. Now, what if we had done for our test, actually done it the other way around? Let's go to stat. Let's get regression, simple linear. And then instead, we chose the chirps in 1 minute as X, and the Y value is temp as Y. What would happen then? Well, what we get is you get exactly the same values, exactly the same correlation, exactly the same p-value. So that really doesn't matter. Okay. Now, for a real life situation, of course, you're thinking if it is cause and effect, we don't know that. Just because we're rejecting the null hypothesis still does not imply that the temperature is causing more chirps, but does suggest there's a relationship there, a linear correlation there, and a fairly strong positive one. So as the temperature increases, number of chirps increases in a minute. But if you switch it the other way, just as far as statistically, just look at the numbers, there's no difference which one you treat as X, which one you treat as Y. So what we've seen today is we learned about creating scatter plots and also learned about correlation. So scatter plots are useful to help us visualize data and hopefully indicate whether, by looking at it, whether there suggests to be kind of a trend. But if there appears to be a trend, we need some way then to actually quantify that, and that's how we do the correlation coefficient. And so once again, it's a linear correlation coefficient. There are other kinds of correlation coefficients for other types of graphs like this, other types of relationships, we didn't consider that here. We learned some important things about these correlation coefficients, specifically that even though if there's a correlation is present that is not clean, there's a cause and effect relationship. Then we learned how to test the hypothesis test to determine whether we can say statistically that linear correlation is present. Thank you. Have a good day.